Hi, me again. Okay. For this current video, I will discuss another problem example about dry friction. And the problem that we are going to talk about is this particular problem. Okay, as you can see there. Okay, so this particular problem. Yep. Please ignore all the writing first. Please ignore the right side first. I want you guys to concentrate on the problem that we are going to talk about. Okay, that one first. Okay, in this particular case, there is a person who tried to fix the electricity at the electricity pole. Okay, and that particular person is using a belt. Okay, and the belt is connected to the person. Okay, like this, and then the belt itself is also connected to the directly connected to the pole at A. Okay, and there is no pin, no such kind of a lock or whatsoever. At A here, there is a friction between the belt and the pole. Okay, and beside that, there is another friction between the shoes of the man with the pole as well. Okay, and there are some known value. The first thing is the weight of the man. The weight of the man is high 80 lbf. Okay, and the center of gravity of the man is at this particular point G. Okay, beside that, it is known as well that the friction between the man's shoes and the pole is 0.6. The static coefficient of friction between the man's shoes and the pole is 0.6. Okay, and the question there is the minimum coefficient of static friction between the belt and the pole. Okay, in order to support the man. So what is the minimum coefficient of static friction at this particular point between the belt and the pole? Okay, and in order to solve that, what we're supposed to do, as usual, always start with drawing the free body diagram. After you know the problem, then we draw the free body diagram. As you can see here, this is the drawing. This is not my own drawing. I use some other's drawing. Okay, you can see here the weight of the man is happening at point G. Then beside that, what we have there is just normal force and friction. The first normal force happening at the belt, okay, between the belt and the pole, okay, going that way, because at this particular free body diagram, what we draw is the man and the belt as one free body diagram. So the system that we are looking at is this particular system, which consists of the belt, the man, and man's shoes, Okay, so as you can see, the normal force is happening between the pole and the belt. So because we are looking at the free body diagram of the man, belt, and shoes, right? So at this particular point, the normal force is happening at the belt in that direction. Okay, and because of there is a normal force, there will be a friction force as well, Fa going up. Okay, then beside that, the other thing that we have is another normal force between the pole and the shoes. Okay, because the free body diagram that we trying to look at is the shoes man and the belt. Okay, so for this one is the friction force which is happening at the shoes. Sorry, normal force which is happening at the shoes, going that way, going to the right. Okay, and because there is a normal force, of course there will be a friction force. But remember, the friction force there, okay, it's supposed to be 0.6 multiplied by the normal force. Why is like that? Because in order to make sure, in order to make the friction, the coefficient of static friction at this particular point minimum, okay, at a minimum, we have to make sure that at this point, because it's going up as well, the friction force which is happening in there is supposed to be maximum. Okay, supposed to be maximum. That's why in that case, we have to make sure that the friction force there that we write there is the maximum, 0.6 multiplied by the normal force. Why 0.6? Because the coefficient of static friction is 0.6. So that's supposed to be 0.6 multiplied by the normal force is supposed to be our maximum static friction. Okay. Then after that, after we draw the complete free body diagram with all the dimension as well, okay, with all the dimension as well, then after that we can use those three equilibrium equation: sigma fx equal to 0, sigma fy equal to 0, and sigma moment equal to 0. Okay, using sigma moment at point A at this particular point. Okay, what we will have there will be, if clockwise is positive, remember clockwise is positive, what we have there will be 180 pound force multiplied by the horizontal distance, this one. The horizontal distance there is supposed to be 2.5 feet plus 0.75 feet, supposed to be 3.25. Sorry, 3.75 feet. So the moment there will be supposed to be 80 multiplied by 3.75 feet. Okay. So this is it. Due to this particular force, then because clockwise is positive, okay, then due to the friction force at point C here, there is another moment. Okay, the moment there is supposed to be counterclockwise because there is a distance here, it's supposed to be counterclockwise. Okay, and the value there is supposed to be Fc multiplied by 0.75 because the distance here is 0.75. Okay, minus because it's counterclockwise. And because beside that, we have as well moment due to NC. And the moment there is supposed to be counterclockwise as well, so it's negative. So NC multiplied by the distance 4 feet. Okay. Then, because we know from the beginning that Fc is equal to 0.6 NC, okay, because the static coefficient of friction is already known, 0.6 from here, okay. Then we can calculate for NC, okay, and Fc here, just replace it with 0.6 at NC. Then the only unknowns that we have there is only NC. You can see here, this is the calculation. Then the results of NC will be this one, 131.46 lbf. Okay. Then using sigma fx equal to 0, the only horizontal forces there are NA and NC there. Okay. So if going into the right is positive, then my sigma fx will be NC minus NA equal to 0. Because of that, we know that the value of NA will be the same as NC. And remember that NC, we already have the value there from the first equation. That's why we get the value for NA as well. same as NC, 31.46 lbf. Then using sigma Fy equal to 0. There are three forces which is going to which has a vertical direction: 100 lbf, 180 lbf, sorry, Fa and Fc. Okay, remember Fc there is we're supposed to replace it with 0.6 Nc. Okay, if going up is positive, we have Fa going up positive, Fc going up positive, and negative 80 lbf because the weight is going down. This one. Okay, and then replacing Fc with 0.6 Nc. This is what we will get. Okay, this is the equation that we will get. And remember that we already have the value of Nc. This one. By putting the value here, okay, we will be able to get the value of Fa. This is our value of Fa. And because our Na value, the normal force value is this at A, okay, we can get the minimum coefficient of static friction at A as well. By, remember, okay, you have to remember that Fa is supposed to be the mu s multiplied by Na. Okay, that's why our mu s at A is supposed to be Fa divided by Na. And remember, both value, we already get both value from the previous calculation. This is our Na, and this is our Fa. Okay, that's why we can calculate for mu s at point A. Fa divided by Na, and the value is 0.769. Okay, decimal. Okay, and this is the answer that we need. Okay, so I think that's all for the solution of this particular problem. Okay, hope it helps you to understand about dry friction. Okay, I think that's all for now. Okay, see you again.